Welcome to the course Business Analytics and Data Mining Modeling using R Part 2. So, in previous lecture we started our discussion on smoothing methods. So, we will continue from there, and this is the last lecture of this particular course, the Part 2 Business Analytics and Data Mining Modeling using R Part 2. So, we would like to complete this particular topic in this lecture itself. So, let us start. So, let us do a quick recap of what we have discussed in previous lecture. So, we talked about smoothing methods, and we said that this is these methods are typically based on averaging over multiple observations. So, main idea is to smooth out the noise to uncover the patterns. So, the patterns could be the time series components like trend, seasonality, label. So, these are the three components. So, we would like to smooth out the noise part and uncover these patterns. It is a data driven, so we do not impose any predetermined structure. So, these things we were able to discuss in the previous lecture. We talked about how different smoothing methods differ from one another. So, few points also we discussed. Then we talked about two important two popular smoothing methods, moving average methods and exponential smoothing methods. So, moving average, we talked about that averaging across a user specified window of consecutive observations. So, typically like we discussed in the previous lecture, typically moving average methods they do not make a distinction between different time series components like label, trend and seasonality. So, therefore, the performance of moving average methods in especially if all three components are present. So, that might not be always competitive in comparison to other methods. So, how do we overcome this? Are there any other methods available to overcome this limitation of moving average methods? So, we will discuss that part also in this lecture. So, centered moving average, so we have discussed this in previous lecture. Trailing moving average also we covered. So, then we talked about in the previous lecture, this is where we ended, that moving average methods they are suitable for forecasting series with no trend or seasonality. This is because typically these methods, because this is based on averaging of multiple consecutive observations. So, typically these methods they do not make any distinction between the time series components label, trend or seasonality, and if trend or seasonality are present, then because of the averaging that is happening, because of the seasonality as we talked about, there are going to be under forecasting for peak season, there is going to be over forecasting for non peak season. So, therefore, time series where seasonality is present, these particular methods might not work as well in comparison to other techniques. Similarly, if trend is present, then also. So, the solution is use de-trended and de-seasonalized time series. Therefore, just use these methods to forecast the label component of the time series where only label and noise is present. So, noise is going to be averaged out because of the characteristic of these methods, because we take averaging of multiple observations. So, noise is going to be smoothed out, and therefore, we would essentially be forecasting the label component given that time series has been de-trended and de-seasonalized, or when the time series does not have the trend or seasonal component. So, we will continue our discussion from this point. So, how do we do this? So, regression based model, just like we have discussed in the previous topic in this module where we talked about regression based forecasting. So, you remember that you would remember that in the bicycle riders data set that we had used, finally we were able to model the seasonality and trend part. So, we were able to find that it was the quadratic trend that was there, and in the month annual seasonality was present there. So, we are able to model that in the regression based forecasting, seasonality and trend both the components. So, therefore, the residual series that we had was actually de-trended and de-seasonalized series. Why not use that series and apply smoothing methods to improve the forecast on the label component, specifically short term forecast on the label component. So, that is something that can be done. So, let us open RStudio and we will do an exercise and do this. So, load this library XLSX, let us import the data set. You can see data has been imported, as you can see in the environment section. This is the structure of the data set, we are already familiar with this. So, I have just created the time series vector for this. So, we will just move on centered moving average and and the trailing moving average, this part we have already done in the previous lecture. So, we will just skip this and we will come to this part where we will talk about the produce a detrended and deseasonalized series using regression model. So, we will first as we did in the in this regression based forecasting methods topic, those particular lectures. So, we need to first create the season variable, right, as you can see here, then length of this this particular data set, then t square will create a data frame out of all these variables. So, this is the data set that we would be taking forward for regression based forecasting. So, this is something that we have done. So, we are doing this regression based forecasting to produce a detrended and deseasonalized series. So, residual series of this regression based model is going to be the detrended and deseasonalized series, and then we would be using this particular residual series to apply moving average model. So, let us do the trimming. So, as you can see like the previous lectures, we can create this model lighters versus t square. So, we are fitting quadratic model plus seasonality. So, let us run this. So, we have got the model. So, from this you can see we are now going to create a time series vector for from the residuals. So, you can see mod dot dollar residuals. So, this is we are going to use this particular vector and create a time series vector for residual series. So, let us have a look at the plot. So, this is the plot for residuals. So, as you can see like we did in the previous lectures on regression based forecasting, the trend component and the seasonality component has been adequately modeled, which is also clearly visible in the in this plot also. And we had also seen in the ACF plot also in the previous lectures that there was nothing outside the bounds, and therefore, those components were adequately modeled. Now, can we use moving average methods to improve the forecast even further? So, this is something that we are going to attempt now. So, we are going to apply, as you can see here, trailing moving average model on this residual series. So, filter is the function like we used in the previous lecture, and we are going to apply this on this residual series, as you can see here. So, let us run this code. So, we get this these values, this vector, and then let us apply this model. First, we will initialize another time series, take the length of the the computation that we have just done, and we are taking this window width as 12. We are taking that the series has annual seasonality, and with this we will use this window and do our forecast. So, this forecast is like we did in the previous lecture using the trailing moving average model, right. So, we are going to take average of 12 values, 12 consecutive values, and going to assign that as forecast for different points in the training set. So, if you are interested in looking at the forecast, you can see that forecast is available from this point onwards, that is 8, 9, 10, 11, 12, 13 points onwards the forecast, because 12 points are required for averaging. So, this is the forecast that we have, and then we can also have a look at the this particular data frame to get the idea about how this trailing model is being used. You can see It is the 13th observation from where we can starting where our moving average model has been applied. So you can see this is the actual, and then the the forecast and the residual. So this is what we have done. So we have applied trailing moving average model on this residual series, and we have got our forecast. So hopefully this forecast is going to further improve the performance of model. So essentially what we have done, we applied regression based forecasting, got the residual series, adequately modeled the trend and seasonal components, and the residual series then we are applying moving average method, so that any short term forecast that could be improved further. So label component, essentially we are working on the label component and trying to improve the short term forecast. So we can have a look at the performance of this model on training set. So you can see here. So for these observations for which we have the forecast available, we can compute the performance. So first we need to load this library K minor R minor. So we are going to do this. So once this library is installed, so this is loaded. So let's compute this. So these are the values as you can see here. We can use these values to compare the performance, how the performance that we had using the regression based forecasting and how it has been improved. So you would see that if we compare these numbers with the numbers that we have just when we just use the regression based forecasting, then whether a moving average method has been able to improve this performance, right. So then for the next point, if we want to forecast the next point, that is April 2016. So we want to create a forecast for that. So this is how we can do it. So this value, this vectors, this value is going to be the forecast for this point. First point, this point is the first point in the test data set. So this is the forecast. Now let's go back to our discussion. Now how do we select window width? So a few things that we have discussed in the previous lecture also. So let's revisit. So this was the point that we discussed. So for a time series having seasonality component, length of seasonal cycle could be a choice for W. That is something that we discussed. The main idea being that we can suppress the seasonality and noise, and we would be able to uncover the trend. So this is mainly kind of rule of thumb for a time series having the seasonality component. Few other aspect about how do we go about selecting the window width W. So few points have been discussed. So as we have discussed before also, W is something that is user specified. Then while selecting a particular value for W, we have to look for the balance between under smoothing versus over smoothing. So we want we don't want to average out everything, otherwise the average series won't have enough information for us to make forecast. However, we don't want to under smooth the series. So we don't want to under smooth the series so that the noises are still present and the forecasting performance is quite bad. So the balance between under smoothing versus over smoothing, that has to be done. So specifically we talk about the centered MA that is typically used for time series analysis. To uncover global trend, we can use high value of W, because global trend that is typically going to be applicable in the longer term. So therefore if we keep the higher value of W's, and the averaging out will happen in more number of observations, and therefore the global trend that is visible, there are more chances that we would be able to uncover that. If we want to uncover the local trend, then probably we would be better with having using the low value of W, because the local aspect of local trend that is present in that particular part of the series, that would be easier to uncover. Similarly, if we talk about the trailing moving average, and which is typically used for time series forecasting. So we have to look at the the relevance of recent values. So how many what is the relevancy of the historical values that are there, whether they are going to help us in terms of improving the forecast, and how the series itself has been changing. So the rate of change of series and the relevance of the recent values, the past values of the series. So that we have to look at in terms of for deciding the window width W. So we can do experiment with different values of W and compare performance of candidate models on validation set. So something like we did in the previous course, the first part where, for example, in Cadence we followed a mechanism where we compared the performance of different candidate models on validation set to find out the best K for the model. Similarly, here also we can do the same thing and try out different values of W and compare the performance of different candidate models on validation set and get the best W for us. However, in such a situation, if we follow that mechanism, we should keep in mind that it might lead to overfitting. So we have to guard for this overfitting scenario as well if we follow this approach. Now let us move to our next next technique, that is simple exponential smoothing. So let us discuss how this particular technique, simple exponential smoothing, is different from the moving average methods. So the idea is in this particular technique, the idea is to give higher weightage to recent values while retaining older information with lower weightage. So if we look at the moving average, what we have been doing, we have been selecting the number of observations and taking average. So we did not make a distinction between which values are going to be more useful in forecasting and which are going to be less useful. However, in this case we take a weighted average in the sense, and we give more weightage to the more recent values and less weightage to the older values. So the exponential smoothing methods, they typically implement the weighted average formulas. So you can see here, weighted average of all past values is taken and weights decrease exponentially into the past. Suitable for forecasting series with no trend or seasonality. So just like for the moving average method we talked about, smoothing methods in general, especially simple moving average methods or simple exponential smoothing method, they don't make a distinction, as we talked about, distinction in terms of different time series components, label, trend and seasonality. So therefore if the trend and seasonality are not present, or the series has been detrended or deseasonalized, so these methods, so these smoothing methods can be helpful in terms of improving the short term forecast. So let us have a look at the expression for simple exponential smoothing. So value of one step ahead forecast f t plus 1 at time t can be computed using this expression, can be written in this form. So f t plus 1 is alpha y t plus alpha 1 minus alpha times 1 minus alpha y t minus 1 plus alpha times 1 minus alpha square y t minus 2. So you can see here that starting from the first term, then the second terms, the weights are continuously decreasing, given that alpha is a smoothing parameter and takes the value between 0 and 1. So because of the value that it takes between 0 and 1, so the second term onwards, the weight, if you just look at the weight from alpha to alpha times 1 minus alpha and so on, the weight will continuously decrease. So therefore we are giving more weightage to the higher weightage to the recent values, that is yt minus 1, and lower weightage to values which will come later, that is yt minus 3, yt minus 4 and so on. So this same expression can be rewritten in this form. So f t plus 1 can be rewritten as this, as you can see, alpha yt plus 1 minus alpha times, and we have taken this factor as common, 1 minus alpha, and in the brackets we get this expression, and this expression can now be rewritten as f t, as you can see here. So this we can see here, this can be rewritten as ft here, and this is how now we can again rewrite this expression. You can see here ft plus 1 ft. Now we are taking alpha as common. Now if we look in the parenthesis yt minus ft, so this is actually nothing but actual value minus the forecasted value. So this is the error part. So the same thing we have written here. This is the forecast error at time t. So in a sense ft plus 1 can be rewritten as combination of ft plus alpha times et, so where et is the error. So if we look at it, the ft plus 1, the forecasted value is actually improvement on the previous value. So value at t plus 1, the forecasted value for the t plus 1 is actually improvement on the forecasted value at t, plus this error. So alpha being the smoothing parameter, and that in this alpha decides the rate of learning. So this learning is coming from this ed, that noise that is component, and how much learning is to be done to be able to make the forecast. So we can see from here. Also if we can see that we can see here k step ahead forecast ft plus k is nothing but ft plus 1. Reason being we don't have any further information to improve this forecast, right. So because of this all 2 step ahead, 3 step ahead, 4 step ahead, all those forecasts are essentially going to be the same as 1 step ahead forecast if we use this expression, simple exponential smoothing equation. Now let us discuss this parameter alpha, smoothing parameter alpha, and how do we go about selecting the value for alpha. So as we have talked about, determines the rate of learning. Is being used for the to compute the weighted weighted average also, and in a sense that also decides. So if the value is near 1, then of course the fast learning is going to take place, because we would be learning more from the these values, the fast values yt minus 1, if the alpha value is close to 1. If the alpha value is close to 0, then the learning is going to be slow, and we are going to learn slowly from the past values. So depending on the scenario, depending on the relevance of past values and the amount of smoothing that is required, we can decide on a value of alpha. And of course just like for the moving average method and the W that we talked about, we can also do experiment with different values of alpha and compare the performance of candidate models on validation set, and find out the best alpha for our problem. However, as we said for window width, here also in this approach also we have to avoid the overfitting. If we look at the default values, typically 0.1 value between 0.1 and 0.2 is considered good for learning in most of the cases. So what we are going to do, we will open RStudio and do an exercise for simple exponential smoothing. So you can see here, so we are going to use the same residual series that we have computed in this lecture. So now we are going to use this Halt-Winters formula. So this Halt-Winters function is actually gives us the flexibility of applying the advanced exponential smoothing. However, right now we are going to just use it for simple exponential smoothing and not for the advanced exponential smoothing. So to be able to use this function for simple exponential smoothing, we need to make these two arguments beta and gamma as false. What these arguments are about, that is something that we are going to discuss in this lecture itself. Right now let us focus on this alpha, which is the learning parameter. So this is the residual series STSV in the first argument, and the second argument we are giving the rate of this learning as 0.2. The smoothing parameter is this much. So let us run this code and we will get the model for our simple exponential smoothing. So let us have a look at the forecast and residuals from this model. So certain computation to compute this table, where we will have these are the actual values from the residual series, and we can see that from second row onwards we have the forecast also and the residual part also. So this is based on applying simple exponential smoothing. Now if we want to plot this, how this model is performing, so let's plot the residual series, let's add the forecast. So this is the plot that we can see here. You can see red line is the forecasted points, and the actual residual series plot is in black color. So you can see how this simple exponential smoothing model, how it has been able to forecast this particular series. We can have a look at the performance, training set performance also here. So you can see that performance is, if we look at the this parameter and the second and third parameter, but the performance has slightly improved from the moving average method. Similarly, if we want to forecast for this April 2016 point, we can use this forecast.halt winters function, but for this we need to have this forecast package. So before we move ahead, let's install this package. So what we are going to do is we'll install this package so that we are able to use this library. So let's type forecast. So this package actually helps us in making certain forecasts using function forecast.halt winters. So we'll just install this and then load this library and use it for our forecasting. This is something that this particular is something that is we are going to use later on for the advanced exponential smoothing as well. So let's do this first. So let's again run it. There seems to be some problem. Let's look at the key for this. So this, as you can see in the help section, forecast.halt winters in the forecast package, this is there, but we are getting some error here for this one. Let's see whether the model 2 was created. So model 2 is there, we are getting this error for some reason. Okay, so let's move forward. We'll get back to this problem, we'll sort it out and get back. Let's move to our discussion on slides. So we'll discuss some more important aspects of smoothing methods. So let's first discuss moving average versus simple exponential smoothing. So if we look at the parameters that are being used in these two types of methods. So we use window width W for moving average and simple exponential smoothing. For simple exponential smoothing, we use this is smoothing parameter alpha. So these are the two parameters which are specified by the user, and in a sense they set the importance of recent values over old values. Let's look at the limitation of these two methods, MA and ES methods. So as we have talked about that these methods are suitable for forecasting series with no trend or seasonality. So that means series would be left with only a level and noise component, because these two methods, as we have discussed, they typically take the average or weighted average of the consecutive values, past consecutive values. So therefore they don't make a distinction, they don't try to identify the label, trend or seasonality component separately. So typically they tend to just forecast the label, so they are useful for short term forecasting. However, we have to make sure that trend or seasonality is not present, otherwise for the performance will take a hit there. So, as we have discussed, one solution is to either detrend and deseasonalize the series using regression model, something that we have done already, right. So, second solution is to use advanced versions of exponential smoothing methods to capture trend and seasonality components. So, there are some advanced versions of exponential smoothing methods that are available, which could be used to overcome this problem. So, this is the second solution that we have. So, that is something that we are going to discuss now. So, this comes under the advanced exponential smoothing methods category. So, we are going to discuss three scenarios here. First one, where the series is having a trend component but no seasonality component. Then a series having both the component trend and seasonality. Then a series having just the seasonality component and no trend component. So, we will talk about the advanced exponential methods, so that could be used for this. So, for a series with a trend component and no seasonality component, we can use double exponential smoothing, as we can see here. So, in double exponential smoothing, what we assume is that trend can change over time. So, therefore, the idea is that there is no global trend. So, therefore, the structure model, the regression based model, probably they are not going to be suitable in this scenario. The focus is on local trend, so which is where this exponential smoothing and in general smoothing methods are going to be useful. So, a local trend and label are estimated from data and updated dynamically. So, if you see this statement in the earlier simple moving average and simple exponential smoothing, we were typically able to forecast the label component, but here in this scenario trend and label both components are estimated from data and updated. So, let us have a look at the equations here. So, this is called double exponential smoothing because we can look at two components. Simple exponential smoothing, it looks at just one component, that is label. Double exponential smoothing, it can look at two components, that is label and trend. So, now k step ahead forecast ft plus k is can be rewritten as this. Ft plus k is lt, that is label component at time t, plus k times a trend component capital T. So, this is trend at time t. Now, how these label and trend component are going to be computed. So, we can see the equations for these two components. Lt can be written as a combination of alpha yt plus 1 minus alpha times Lt minus 1 plus t capital T minus 1. So, you can see in the first part alpha yt we are using the actual value to define the label plus the previous value is also there Lt minus 1. So, that is also here and an adjustment using the trend. So, trend component is being used to adjust also and the actual value is also being used to dynamically determine the label at time t. Similarly, for trend component you can see here the second part 1 minus beta times capital T minus 1. So, the previous value of the trend is also in a way determining the trend at time t, and also from the label also the difference in the labels, that is also being used to determine the trend at time t. So, dynamically it is going to be determined. So, in this fashion we can compute the k step ahead forecast. Here from this you can clearly see that now one step ahead forecast, that is ft plus 1 is not going to be equal to forecast at t plus 2, ft plus 2, ft plus 3 and so on. Reason is obvious because now trend component is there which is going to vary, right, which is going to change. Now, we are going to use two smoothing parameters alpha and beta. So, these parameters are respectively to be used for label and trend. Now, second scenario where if both trend and seasonality both the components are present, then the Halt Winters exponential smoothing method that could be used. So, this method we saw in the R studio also, where we had the arguments for beta and gamma. So, now you can see that beta is for the trend component and gamma is later on we will see is going to be used for the in this scenario itself we will see it is used for the seasonality. So, 3 smoothing parameters are to be used now, one for label alpha, one for a trend that is beta, one for seasonality that is gamma. So, this Holt-Venters exponential smoothing is also an extension of double exponential smoothing. So, let us have a look at the some of the expressions for this. So, now we can see k step ahead forecast f t plus k, and these equations we are writing for multiplicative seasonality. So, we are assuming here that multiplicative seasonality is present. So, therefore, values from one season to other seasons are changing in percentage amounts. In additive seasonality they change by a constant amount, but in multiplicative seasonality it is they change by percentage amount. So, therefore, we multiplied by that factor. So, you can see f t plus k, and we are multiplying by this seasonality factor to compute this value. So, f t plus k can be written as labeled component L t plus k t trend component, and this whole expression is multiplied by the seasonality value index, seasonality factor f t plus k minus m. This small m is actually indicating the presence of seasonality with m seasons, right. So, from there here we will also see that to be able to use this expression, the t value should at least be greater than m. So, that this this s could be meaningful there and could be used to compute this f t plus k. Similarly, if you see the label at time t, so there is some change in this expression. You can see now we are adjusting for this multiplicative seasonality. So, first term alpha y t is now divided by this capital S t minus m value, plus the second term is as is L t minus 1 plus t minus 1. So, label is being adjusted by the trend itself, and also the actual value is being adjusted by the seasonality. If we look at the trend component, it is same like it was in the previous scenario. If we look at the seasonality component, now how we can see the gamma is the smoothing parameter here, and we can see in the first expression seasonality is being determined by the actual value, but after adjusting for the label. The second component in this is this previous seasonality value, right. So, we can see as t minus m. So, this is how these are the equations that can be used if the multiplicative seasonality is present. Here also these one step ahead forecast, 2 step ahead forecast, all these are going to be different, and as we can see alpha, beta and gamma are the smoothing parameters for label, trend and seasonality respectively. Now, third scenario where the series is having just the seasonality and no trend. So, the same expression that we have discussed, the Holt-Venters exponential smoothing method, the same method can be used. We just need to delete the trend trend terms in the equations. So, if we do this we will have these equations as you can see here, k step ahead forecast, label and the seasonality, and these are the equation that can be used. So, with this we have covered the advanced exponential smoothing methods also. So, let us go back to RStudio and do an exercise for advanced exponential smoothing also. So, let us also hope that maybe this forecast dot Holt-Venters this will work this time. So, first we will create a TSV time series vector time series object for the training set. So, you can see here we are using this df train riders which was already trained. So, we will create a time series object from here. Now, the Holt-Venters function we are using, now you can see the argument alpha is specified as 0.2 for label, beta is 0.15 for the trend, and gamma 0.05 for the seasonality. You can see the seasonal we have specified as the multiplicative, start dot periods has been specified as 12. So, we are specifying annual seasonality here. So, we can run this function and we will get the model. Now, we can summarize the results for this. So, you can see from 13th row onwards we have the forecast and the residual numbers here. So, let us plot these numbers and see how we are able to forecast. So, this is the TSV train, this is the So, this is the right now let me tell you that this advanced exponential smoothing, this is being done on raw or original series, right. So, all this is on original series. So, advanced this particular function, Halt-Winters function is going to deduct all components from the data itself. So, this series we already know, this bicycle data set we already know has a trend and seasonality component. So, that is why you saw that we had specified alpha, beta and gamma while modeling. So, let us plot our forecasted values. So, we can see in this plot the actual values and the forecasted value also. So, we can see the forecasted value are quite closely following the actual values. So, you can see the Halt-Winters function can be used to forecast the series with trend and seasonality component as well. We can have a look at the performance. You can see performance is less than, so you can see second value MDAE, this value is even less. So, the comparable performance can be seen, something that when we use regression based forecasting and then applied trailing moving average, and the performance was similar to this, and in this case also similar kind of performance we are able to see. So, this was the performance on the training set. So, for the test set also we can do this. So, again let us hope that forecast this works this time. So, it is not working for some reason. However, if we use this function, we will get the forecast for next well, and then we would have been able to see the results for the test set as well. So, that is left for you to complete this exercise, and we can also have looked at the plot for how the model is performing on the test partition. So, let us go back. So, we have been able to cover this smoothing methods. So, that completes our time series modeling as well. So, in this particular course business analytics and data mining modeling using our part 2, we have been able to cover both the modules unsupervised learning methods as well as time series forecasting. So, with this we complete our course. Hope you enjoyed the course. Good luck for future. Thank you.